Good afternoon. I will be talking about our development of wavefront sensing and ultrafast AO for imaging the living human retina. Starting from motivation, I will describe our ultrafast AO system. Then I will talk about ocular aberrations in clinically relevant scenarios and show the benefit of using faster AO. Here's a simplified schematic of wavefront sensor-based AO systems. A Sharp-Hartman wavefront sensor is used to measure the residual aberration after a wavefront corrector. Because ocular aberrations change over time, an AO system should run fast enough to keep the residual aberration low. Today's ophthalmic AO systems are generally designed to correct dynamic aberrations up to 1 to 2 Hz. However, this design is based on ocular aberration measurements acquired in healthy subjects under ideal conditions, which do not capture many real-life clinical scenarios that can induce both high and low temporal frequency aberrations. I will show some examples later. For clinical use, AO should satisfy several criteria. It should quickly align to the patient and allow rapid focus through and about the retina. It should stabilize focus at the retinal depths of interest. It should minimize the impact of tear film disruptions, eye blinks, and eye motion to allow continuous data acquisition for simple and high throughput imaging in the clinic. It should correct accommodation. These criteria become more stringent in the presence of disease and aging that exacerbate conditions such as dry eye, reduced fixation stability, and nystagmus, prohibit cycloplegia in some patients, such as those with narrow-angle glaucoma, and cause abnormal optics requiring contact lens correction. These conditions necessitate higher AO speeds, as supported by the data I will show. To address this need, we develop an ultra-fast ophthalmic AO system. Key to our system is a low-latency, photon-efficient wavefront sensor, which uses 20 by 20 lenslets. To reduce the latency, we use a wavefront sensor integration time of 0.126 milliseconds, which is 100 to 500 times shorter than commonly used in the field. Our wavefront sensor camera has a readout speed of 1.4 gigapixels per second, which is 3 to 100 times faster. The frame rate is up to 342 Hz. Even with the short integration time, our wavefront sensor captures 2700 photoelectrons per lenslet per frame, 27 times more than the photon count used in astronomical AO. Here's a photo of our wavefront sensor. Different from astronomical AO, we use a discontinuous exposure scheme permitting a high AO loop gain of 1, which helps increase the AO bandwidth. We use a high-speed deformable mirror. To reduce the DM activation effect, we optimize the delay between sending control commands to the DM and the start of the wavefront sensor exposure. After we build the system, we characterize the temporal performance of our AO system. After AO onset, the RMS wavefront error reached diffraction limit in about 5 milliseconds, even in eyes that are not cycloplegic. We simultaneously acquired AOCT cone mosaic image, which share the same time axis as the top plot. The image confirmed a quick reduction of aberration due to AO. To characterize the temporal performance of the AO system more comprehensively, we measure the power rejection curve, which show the aberration power reduction ratio as a function of frequency. The lower the aberration power reduction ratio, the better the AO correction. When this ratio is no smaller than 1, the AO system can no longer correct aberrations. Hence, the AO bandwidth is defined as the frequency when the aberration reduction ratio reaches 1. The bandwidth of our ultrafast AO is 37.5 Hz, much larger than the bandwidth of the mimicked conventional AO. At low frequency, ultrafast AO reduces aberration power density 500 times better. For our mimicked conventional AO, we use an integration time of 45 milliseconds and an AO loop rate of 10 Hz, which are the average parameters of two most widely used ophthalmic AO systems in academia and industry. We can compare our AO system with reported ophthalmic AO systems. By comparing speed-related parameters such as integration time, data processing time, latency, time to reach diffraction limit, and AO bandwidth, ultrafast AO outperforms conventional AO by an order of magnitude or more on key speed metrics. Because our wavefront sensor uses a very short integration time to reduce the latency, we need to understand the noise performance of our AO system. Our Sharp-Hartman images show, our wavefront sensor images show well-defined focal spots in all tested subjects, even though we use a short integration time. From these images, we can compute photon numbers and other parameters. Then we can compute the wavefront sensing error due to photon shot noise and camera noise using these equations. The results for 6 subjects show that the wavefront sensing error due to photon shot noise is 9 times larger than that due to camera noise. To understand how much wavefront sensing error is propagated through the AO loop and contributes to the residual wavefront error, we calculate the noise transfer function. Although ultrafast AO uses a high AO loop gain of 1, the noise transfer function shows almost no amplification of noise. In comparison, conventional AO amplifies noise more due to its longer latency. Considering both the wavefront sensing error and the noise transfer function, we calculate the RMS wavefront error due to noise to be 7.4 nanometers for 6 subjects, which is much below the diffraction limit. Hence, the noise causes essentially no degradation of AO performance, and our wavefront sensing is photon efficient. Then, we use our high-speed wavefront sensor to characterize the ocular aberration dynamics in multiple clinically relevant scenarios, which is poorly understood. We measured ocular aberration over 5 seconds and computed the power spectrum. These are the power spectra for 5 subjects acquired under a normal condition where AO systems typically operate. They are below this line showing that conventional AO is fast enough to reach diffraction limit. These are the power spectra in 5 clinically relevant scenarios, which included an eye with nystagmus, a blinking eye with artificial tears to reduce the effect of dry eye, an eye fixated at 4 locations sequentially to mimic imaging multiple locations within a 5-second acquisition, a blinking eye with contact lens, and accommodating eye. The power spectra of these clinically relevant scenarios are 1 to 2 orders of magnitude higher than normals, and they are above the diffraction limit line for conventional AO. Hence, we need faster AO to achieve a sufficient aberration reduction in order to achieve diffraction limit performance. To understand this better, here we show simulated power rejection curves of AO systems with different loop rates, ranging from 10 Hz to 250 Hz. We find that faster AO not only corrects aberrations of higher frequency, but also corrects aberrations orders of magnitude better at lower frequencies. This is very helpful because ocular aberration have more power at lower frequencies. By multiplying the ocular aberration power spectrum with the power rejection curves of the AO system, we get a power spectrum of the residual aberration, from which we can calculate the wavefront error due to finite AO speed. Here we show predicted wavefront error as a function of the AO loop rate. We find that conventional AO is too slow to achieve diffraction limited performance in these clinically relevant scenarios. For example, for the eye with nystagmus, which is this black line, AO needs to run at 110 Hz in order to achieve diffraction limited performance averaged over 5 seconds. By contrast, ultrafast AO can achieve diffraction limit in all these scenarios. Next, I will show I will show experimental results comparing the performance of conventional and AO and ultrafast AO in retinal imaging. This figure shows the AOCT co-mosaic images of a non-cycloplegic eye reopened from a blink with acquired with either conventional AO or ultrafast AO. We see that ultrafast AO achieves good image quality much faster after the blink. The RMS wavefront error as a function of time shows that ultrafast AO reached diffraction limit 14 times faster than conventional AO. Because the system converges so quickly, we can use the data almost immediately after a blink. This can be particularly helpful in subjects with dry eye and require frequent blinking. Contact lenses are notorious for moving about on the cornea, especially after a blink. We image a myopic subject who wore a contact lens of minus 6.5 diopters. After the blink, ultrafast AO achieves better image quality. The wavefront error curves show that ultrafast AO reached diffraction limit 11 times faster than conventional AO. This immediate recovery from blinks enables near continuous data acquisition for simple and high throughput imaging in the clinic. In this example, artificial tears were used to reduce the effect of dry eye. After a blink, ultrafast AO reached diffraction limit 15 times faster than conventional AO. After reaching the diffraction limit, the mean wavefront error for conventional AO went above diffraction limit at around 1.5 seconds. Ultrafast AO also converges much faster after imaging locations changed. We ask the subject to sequentially fixate for 1 second at each of the 4 locations of this fixation target. When the subject changed his fixation location, the wavefront error went above diffraction limit for both conventional AO and ultrafast AO, but the wavefront error was much higher and stayed high much longer for conventional AO. In between changing the fixation locations, large wavefront error spikes above the diffraction limit were observed with conventional AO, while the spikes with ultrafast AO were always below the diffraction limit. Because the system converges so quickly, we can use the data almost immediately after imaging location is changed. This increases the imaging throughput. Imaging in eyes with fast and large eye movements such as nystagmus is a key challenge for current AO systems, as pointed out by many experts in the field. We found that ultrafast AO can better correct aberrations in eyes with nystagmus. This video shows the eye motion of the subject. We performed the AO imaging, and this figure shows the histogram of the wavefront error. Compared with conventional AO, ultrafast AO achieves a lower wavefront error with a mean about half of that of conventional AO, and a stride ratio about more than 2 times larger than conventional AO. Here we show the cone mosaic videos acquired from this eye. In many frames acquired with conventional AO, the image resolution is not sufficient to resolve the cells. By contrast, ultrafast AO consistently achieves good resolution. Both videos have comparable eye motions, such as microsaccades, that are not correctable with AO. Ultrafast AO also enables a more stable focus in non-cycloplegic eyes. These videos were acquired with the system intended to focus at the inner plexiform layer. Each image is the projection of a volume along the faster scan axis. The focus depth fluctuates over time with conventional AO, while the focus depth is much more stable with ultrafast AO. The stable focus provided by ultrafast AO enables fine focus control in the inner retina of non-cycloplegic eyes. Here we focus light at 11 depths sequentially from IPL to NFL with a step size of 7.4 microns. We can see a difference in the AOCT image even when the focal shift is only 7 microns. In summary, we developed low latency, photon efficient wavefront sensing and use it to achieve the fastest ophthalmic AO that we know of. Compared with conventional AO, ultrafast AO increases the AO bandwidth by up to 34 times and improves the aberration power reduction ratio by up to 500 times. Using the ultrafast system, we characterized the ocular aberration dynamics in clinically relevant scenarios and observed 1 to 2 orders of magnitude higher power spectra, showing the necessity of faster AO. Compared with conventional AO, ultrafast AO provides much faster convergence after blink, much faster convergence after imaging location is changed, better correction through a contact lens, better correction in eyes with fast eye movements such as nystagmus, more stable focus and fine focus control. Because ultrafast AO reduces the impact of eye blinks and eye motion, it enables near continuous data acquisition for simple and high throughput imaging in the clinic. I want to thank my lab mates and the funding from NIH. Thank you for your attention.